So this is how fast we can brew. This is a little bit of a performance tour. I don't really work on packaging systems these days, so this is a talk mostly from the perspective of a user waiting for Brew install to finish executing. One day I was very curious why Brew was taking so long. I just want to level set before we get into it. This is not a critique of Brew. This is sort of looking at the characteristics of how Brew works, and it has similarities to a lot of other package management systems and how we might look at them. This is also not a serious performance talk. I re-implemented some of Brew and tried to look at various different performance characteristics and then present them in this format. I do not use rigorous benchmarking practices, although I think for the most part I tend to be pretty conservative, so hopefully the benefits are greater than what's being presented here. This is also a small subset of packaging performance, but luckily the 3 previous talks covered almost all of the rest of it, so we're good. This is there's a little key here, just some colored boxes with where these execution steps are happening. When I run a brew command to install the incredibly valuable program cowsay, this is generally what Brew does. It will fetch the entire homebrew package definitions, along with potentially some other ones, inventory your installed formulas and check for ones that are outdated, and then install the program you asked for, optionally install outdated components, and checksum all installed files in some cases. So we're just going to look at the install step. But if you are a stakeholder in this talk because you're curious about why you're waiting for Brew, those other things are going on as well. Just to break this step down even further, Brew maintains a 25 megabyte file called formula.json that has all of the formulas, and Homebrew has taken the Ruby definition of each Homebrew formula and turned it into a JSON output and hosted online. Also worth noting, just very quickly, that this install step is sort of really the happy path of installing a package from Homebrew. If you have to build from source, or if you are not using an operating system that's represented in their build cache, you're going to have to build things. You might also be installing an end-user application instead of a binary or a library, and those steps are going to look a little bit different. But if you are just installing an executable binary, you're going to look like this. So we're going to fetch all formulas, and then we're going to find the formula that we're looking for by name in this huge file. And then we're going to grab the manifest file with various metadata related to the program we're installing, and then we're going to grab a blob of the pre-built artifact, extract and write it to disk, and then symlink everything that we need from that extracted set of files into the appropriate places in our brew cellar. OK, so moving on from cowsay to something with a little bit more dependencies. This is roughly the execution steps in Brew when you install Ruby. You have a few steps to to resolve the relevant dependencies. Unlike the more complex resolution situations we were talking about in the previous talks, Brew is a fixed package tree. So there's no resolution. All we're doing in these steps is finding the metadata for the listed dependencies for something we're trying to install. Then we're going to download the metadata file and all the resulting program files that we need to download for each dependency for all packages. And then we're going to extract them under our file system. So I wrote an experimental version of this functionality that executes the same steps and ends up writing the same files to disk. And then I cached all network calls to attempt to see what the performance difference would be not considering the network. And just sort of a straightforward implementation in a compiled language. that doesn't do all of the steps that happen in Brew, but results in the same files on disk, was able to save close to 50% of the time. I know that alone, the interpreter overhead of Brew is 1 second. So there's certainly a cost here of using a dynamic programming language. And I'm sure there are a few other things going on as well that are slowing it down. For the next sort of few slides of performance, we're going to use this blue bar, where when I did use the network with my version, it took 17.47 seconds as compared to 120 seconds with Brew. This was using airport Wi-Fi, so very performant. OK, so if we want to improve from our 17.47 seconds, the first thing we can do is parallelize. So we have to resolve the dependencies serially, because each step depends on the other. But then the moment we have the list, we can just go download all those files with maximum parallelism. And then when we get to the next step, we can extract everything in parallel. Just doing this very naively gets us to a pretty massive speed up. This is also in a pretty contrived case. If we were installing hundreds of packages with tons of dependencies, we would see a much greater difference. And then moving on from that, this is quite contrived. However, I think this sort of like staging of installing a package does seem to be somewhat commonplace. But we don't have to wait for all the downloads to complete to extract all the files. We can just batch those up and do them in dependency order one by one, which gets us an additional 10% speed up. To some of the things Kat was talking about, we can take this way further. We can optimize the network step and parallelize as much as we can. We can look at the overhead of extraction and make sure that we're considering the CPU cost of decompressing a compressed artifact, and then also the syscall and IO overhead of writing tons of files to disk. And then we can individually think about efficient ways to write hundreds of symlinks, because that's how Homebrew works, and optimize that individually as well. And I'm sure that would get us to even greater performance gains. But this is what I got to in my version. That's mostly it. We switched to a compiled language, and we parallelized everything, and we ignored some of the checksumming and bookkeeping that Brew does. And we wrote something in an afternoon instead of maintaining it over more than a decade. These are so that's all I got in my complete version, but there were some side quests along the way, and I sort of like went down a few rabbit holes of performance to see what sort of uncommon and exotic things you can do. So there's this paper called The Tail at Scale that talks about reducing tail latency at Google. And one of the things they do is if they make an HTTP request or any kind of network request, and they don't get a response in a certain number of milliseconds, you fire off a second HTTP request to attempt to see which one is going to return the fastest. Just first of all, don't do this unless you know that you can abuse the server that you're hitting, and that actually terminating the request will not result in a bunch of additional work or HTTP2 overhead. So this provided somewhat of a shocking, just straight up speed up in requesting small files, which is sort of a blocking step in some of our operations, which is very nice. But additionally, the tail latency improvements for this are quite stark. I think also that there's some benefit here to the way that Homebrew works because of how their content is served. So you might not see as large of a benefit elsewhere, but this was super fascinating. Sometimes when you're installing dependencies, you might have to install Clang, and then it's just going to stretch out, and you're going to wait for it independently while all your other requests are finished. You can sort ahead of time and sort of bin pack your packages the best you can. But I tried experimenting with HTTP range requests and was totally unsuccessful because it was very complicated. But instead, I made this pretty diagram. And you could take your really long, huge file and you could chuck it up into tiny files. Then you could pack it into a small thing, so you don't have to wait for that one dependency 50% of the time. Totally looking at you, Docker. This was also very interesting. When I'm on my computer in an airport, compression and my CPU are way faster than network. They're super fast. We should compress everything. But then when I switch to a data center, I wait like 100 milliseconds for my download, and then the decompression step is just like peeling off into the distance. And so I didn't get time to experiment with this too much. But sometimes your network is way faster than your CPU, and presumably off into the future, once we figure out some crazy single core trick, this might become even more and more applicable. If we just like totally, if we're like, hey, we want to install a program and we just want to execute it and you can do whatever you want, Distry was an experimental package management system that worked by just downloading squashfs file systems and then mounting them in Linux. So this means that all you have to do is download the file, and then you just mount it, and then when you, this only works on Linux, and then when you're reading the file system, you're just reading right into the immutable squashfs file system. You get immutability out of this. You don't have to decompress. I'm sure there is some I/O overhead, or maybe there isn't. I'm not entirely sure how squashfs works. It's fast in my experience, just executing a program. And then some work out of Google with this star GZ. It was very interesting. You basically mount a Fuse file system, and you just start your container, and then you wait for open calls. And when somebody requests a file, you just fetch that file from the network while you're downloading the remaining files. So you can just start executing your program, and you wait for syscalls in the file system, and then you fetch whatever is needed just in time for execution to continue. So if you really care about cold starts, and you are comfortable mounting everything on Fuse and doing this kind of thing, might be applicable. Super fascinating. I spent a lot of time trying to get file system performance faster. And it was very hard, and I basically could not. Executing all file events in a single thread, or not really in a single thread, but just sort of executing them naively was totally fine. But NVMe and IRU ring are here, and especially if you were doing a lot of I/O, there is just sort of a huge amount of space in the performance stack of being able to write a lot of files to disk in parallel. So I think today, writing files to disk can be done pretty naively, especially because most of the time you're just working with the page cache. But if you are downloading a ton of files or doing a ton of I/O and you're really trying to write a lot of files to the file system, pretty excited about some of the stuff that's being opened up by these two. So that's it. Brew can definitely be faster. Although I just want to note that it's a huge project with lots of priorities, and performance is just one of them. I hope that I have to wait less for Brew in the future, but also it's okay. And that's it.
Thank you for that, Max. As I mentioned earlier, we're kind of running behind time, but you've pulled it almost all the way back, so that's fantastic. We'll take a couple of questions.
So you mentioned that you have to install the dependencies serially because one depends on the other, but they're a DAG, right? So some of them could be parallel just because of that. And then they're also binaries by default in Brew, right? So can't you just pour them and they don't need to use each other while they're being installed?
Yeah, sorry. So the only serial step was just the step where it's like, oh, you want to install Ruby? What are Ruby's dependencies? What's the metadata about those dependencies? And then after that, you just have a list. And there's no, since we're not building and there's no build dependencies, there's no DAG. It's just flat,
Thank you for the talk. So I have two historical explanations for why Ruby is not, or why Homebrew is not very fast. One is that we couldn't figure out how to do Control-C correctly when doing multi-threading. because it was written 15 years ago and Ruby wasn't so mature back then. And the other is basically the progress bar. Neither of these are good reasons. I think, if you can make the progress bars pretty like Docker does, you should submit it as a PR.
Thank you. This is the moment I was hoping for in this talk. I also wanted to add to that if you plan on doing anything that I did, don't, because all of your Homebrew's dependencies are hosted by GitHub. There's also a bunch of stuff in GitHub issues about not abusing their network. So please do this, but then bring your own CDN to the table.
Okay, as I said, I'm running behind, keep repeating myself, but thank you very much for that talk.